Microphysics and Cumulus parameterizations, because these are very sensitive parameterizations for the tropics. So I come from the National Astronomical Research Institute. So it's an astronomical institute, but we're starting to go also into atmospheric science research because aside from atmospheric science having more social impact, it also helps the astronomical observations that the institute is doing. So this work is a collaboration with Dr. Jerry Magasa over there from University of the Philippines, where I came from before, and Dr. Tiranan Sotia.
But your PhD is from Germany, huh?
Yes, from University of Bremen.
Ah, I see.
In the north. So first, I'll just introduce the institute. So the National Astronomical Research Institute. So it's like a half government, half private institute. So it's called public organization, not really a government institution. So conceptualized or funded mostly by the Ministry of Science and of Technology in Thailand. So our home base is right here in the northern Thailand, and we also have in this province in Chiang Mai, Thailand. So there's also this big observatory, the Thai National Observatory, which is situated here. And aside from that, there are also other observatories like they call regional observatories for the public, so located in the several provinces. So the one near Bangkok is this one, and also in the northeast and also in the south. So this is mostly for the public to increase their awareness into astronomy and also to get the science culture instilled in the people. And then aside from that, there are also some observatories in other countries, like this one in Chile. Okay, so one of the main problems in terms of atmospheric science in Thailand, of course, is the haze, which is due to the lots of biomass burning that's coming from the central part, also from the northeast part. And so most of the time, especially during this season, these months, so these biomass burning or this haze gets transported mostly to the north. And because the north is mostly mountainous in terrain, so it's lots of mountains there, so some of these haze gets trapped, and it's also a big issue with regards to health. And that's why the institute, which is mostly an astronomical institute, started to do also some atmospheric science stuff. Okay, again, to have some social awareness, okay, to have more social impact on especially on the research. So the institute, or NARIT, just recently commissioned and started the high performance computer cluster, okay, just maybe 1 year ago, and announced to the Thai astronomical community and opened for community use in July last year. So the basic, so this is physically how it looks like. So I'm not a computer scientist, so I have few knowledge about some of the hardware, so I just use it and complain sometimes. But it's okay. So far it's working pretty well. So right now it has 5 compute nodes and having a total of 80 cores, and the expected the speed would be around 2.26 teraflops. So current software that's installed there, they are following, and then just recently we also installed the weather research and forecasting software for the modeling and forecasting. So in Thailand, actually, there's a consortium called the Thai National E-Science Infrastructure Consortium, which was, I think, explained in this morning's talk, and it's like a cooperation of different institutes to have these different high-performance computing clusters. And so far, this is the total. And we just NARIC just joined last year, okay, with an additional computing cluster there. The NARIC, as you saw earlier, it's just started, so you see the number of cores is still pretty small. but it's planned to be upgraded. Actually, I think by next week it will be started to be upgraded and eventually come up with more servers and all that. So this is the plan or the phase 2 architecture for the upgrade of the high performance cluster. Okay, so again, so there's like this new like a marriage, or what should I call that, between astronomy and atmospheric science. So particularly because one of the ways that atmospheric science can help astronomy is to assist the astronomical observations. Of course, they need clear skies when astronomers want to observe. And another one is looking also at this astronomical scene forecast, which I will talk about more later. And the NARIC also plans to come up with to build a big radio telescope, maybe in the next few years. I think one also of the biggest in Southeast Asia. And in the radio astronomy, the water vapor profiles are quite important because the water vapor actually attenuates the radio signal. So it's very important for radio astronomy. So what I will present is just the first phase of the atmospheric science project, which is basically a model sensitivity of the dwarf model to northern Thailand, and then later add more about aerosols. So this is to address the issue of the haze in terms of health and also with astronomical observations. And then later on for the phase 3, like feedback, so because we are an astronomical institute, so we also want to put some astronomy there, so like feedbacks from space weather, particularly solar variability, for more fundamental science applications. So one of the important things for astronomy is, of course, this parameter is called astronomical seeing. So as you can as an example here, so if you, let's say, you have this telescope here, and then you try to image Jupiter. So if there's not much turbulence happening, you will get something like a clear image. However, if you're, let's say, observing at site B and still also imaging, let's say, the same astronomical object like Jupiter, and in this side it's more turbulent, then your image will be more blurred. So it will also be good to, let's say, characterize and forecast the astronomical scene for a particular site. So you know, so that can be used by looking at the turbulence parameters. You can look at the wind profiles. You can model the wind profiles and come up with forecasts, and eventually come up with a forecast for astronomical seeing. So an example, so this is the real data. So this is, I just downloaded a while ago. This was from the Thai National Observatory, and so this is the astronomical seeing. So a good value, I mean, for observers, let's say to have a good image of Jupiter, usually it should be below this black dashed line here. So here, this was in yesterday night, so it was quite high. So that also means that during this time there's more turbulence and then lesser turbulence here. So all the observers also look at this parameter to see whether they have a good chance to do observations. Okay, so just some basics about numerical weather prediction. So, so basically you have this very basic equation. So important thing is your forecast is also dependent on the previous state of the atmosphere, plus some driving forces that you have here to come up with a forecast. And these driving forces, these are usually governed by some of these physical equations, which are called the primitive equations, so equations for wind, temperature, moisture, for water vapor, and so on. So as you can imagine, a lot of complex calculations are involved when you try to forecast the weather. And just like what we saw earlier in the earlier talk, so usually the models are divided into grids, and usually we start with the global climate model data, and then we try to downscale it, or sometimes called dynamical downscaling. So we try to downscale it so that you can have a more focused area with a higher resolution. So from global climate models, we come up with a regional climate model. And one important thing for models is sometimes even if you do the dynamical downscaling when you have the regional climate model, there are still a lot of processes that are smaller than the model grids. So you cannot resolve this like these small processes. Okay, for example, like cloud processes, so these are smaller usually than the model grid. So what is usually done? So is to find out what is the aggregate effects, or if you combine all the effects, let's say, of these cloud processes, what is the aggregate effects? So this is called this parameterization. And some examples of processes that are usually parameterized are these. So lots of small-scale processes. However, for the tropics, so we just usually concentrate on, let's say, the following processes, and these are usually called these microphysics and convective processes. And this is the ones that I did a sensitivity analysis on for northern Thailand. So a microphysics process deals with, let's say, the different, they call condensates or hydrometeors, so examples of which are, let's say, water droplets, ice crystals, hail, and so on. So what are the processes involved, let's say, from let's say forming the cloud until it precipitates, or until it rains. So what are the different processes that come in there? So these are an example of some of the microphysics processes like rhyming, melting, condensation, and all that. So these are all like complex processes that we have there. And in numerical weather prediction, so there are already lots of studies. They come up with some models of the microphysics inside clouds. And these are just some examples that are used. So Q there are the different condensates or hydrometers. So QV is, let's say, the water vapor, so cloud water, rain. And some schemes are more complicated. So this is like the basic scheme, or one of the first schemes that was made, and then it became more complex and more complex, okay, until you have a more complex or a very complex microphysics scheme, or microphysics parameterization scheme. And then the second one are convective processes, or Cumulus parameterizations, and this usually consider these processes, especially when clouds are formed. So how are clouds formed? So first you have an updraft, and then sometimes some entrainment or transport of air masses through the clouds, and then on top you have entrainment and compensating subsidence and downdrafts, and the result is precipitation out of these different convective processes. So basically how clouds are formed. So some of the parameterizations that are used are this one. So these are after some studies. So these are authors and scientists who did a model, who made a model of the cloud. So this is called the Betz-Miller-Janjic. So usually you have these as names. So if you want to, let's say, improve their model, then you usually have your name there as well. So that would be good too. So this is an example, and this is another example, the Cambridge parameterization scheme. So I won't go into details about this. Okay, so the model that I was using I used was the weather research and forecasting model. So it's quite popular, and it has a good community already among researchers, so it's easy to interact. And if you have some problems, you can always like ask some of the scientists who developed the model. So the main thing here is it uses gridded data, okay, and terrestrial data, and comes up. Then you can also use observational data to improve your forecast. So you have some data assimilation also there, and then you have your model out there, which will do all the calculations. You can include chemistry for pollution studies, You can add some fire modules if you want to look at, let's say, biomass burning and all that. You can also do like some idealized experiments. It also has ideal data that you can also use. And one of the important things also for the WARF, it also has some post-processing and visualization software. So I will show you maybe one example wherein we use the Vapor software. So Vapor actually stands for Visualization Analysis Platform for Ocean Atmosphere and Solar Researchers, or for Vapor. So we were talking about using the VR a while ago, so we were thinking about maybe this can also be used as part of your of the VR. So it would be good to visualize. Let's say in this case, for this example, it's like a tropical cyclone, and then you have, let's say, biomass burning, let's say here in the area of Indonesia, and then some of the haze actually gets transported up to the stratosphere with, using by using this visualization, as you can see there. Using this visualization, you can clearly see like what the processes are happening. So the Vapor software is actually a free software. You can download it from here, and it just uses the output of WARF. So directly, you can just load it into the software, and you can change your angle and timing, what variables you want to see. Okay, so the domain that I used is this one. So the big domain is quite big because I wanted to capture almost all of Southeast Asia, but the main focus is in this area. So actually, I could have used a smaller domain. However, I wanted to at least include the whole of Southeast Asia. So this is the outer domain, or these ones would like be your boundary conditions, and these ones will be the outer domain, and then nested domains here towards northern Thailand. So the boundary conditions that I used was from it's 1 degree and 6 hourly data, and then 50 kilometers in the outer grid, 3 hourly output, and for the whole of Thailand is 10 kilometers, which is the same that the Meteorological Department of Thailand is using. And then further to northern Thailand, so I used the 2-kilometer resolution. So for the 2 kilometers, so sometimes, so I said earlier, sometimes you have these convective parameterizations. However, if your grid size is quite small enough, or can resolve these small-scale processes, then you don't need these Cumulus or convective parameterization schemes. So I tested the model for the parameterization schemes for different seasons of Thailand. So in Thailand, actually, there's 3 seasons. So actually, in Thailand, there's a winter, in which before I didn't believe, because I know that Thailand's always hot. But when I was there, so it also reached maybe the same weather conditions as we have now here in Taiwan. So they have a full dry season. So I used this time period, a hot dry season. So I wanted to first use like 3 months. However, I had also an issue of memory and space on the cluster. So that's also one of the issues why I had to drop down the time period here. And hot dry season. And then towards the end, when I was simulating this, I ran out of space as well with the output. So I had to drop down some of the time period that they have there. So the different parameterizations that I used, so these are just the combinations of the microphysics and Cumulus parameterizations that I used are this one. So the default parameterization used by WARF is this one. So it uses this microphysics scheme and this Cumulus scheme. And then from literature, I also looked at that, well, at least for Thailand, the best they said from previous studies are these combinations. And then I tested other combinations as well. So validation sites, so to compare the model data with the observations, I just used 3 sites from the Thai Meteorological Department. So of course this depends on the data availability of the site. So all of these are northern Thailand, but I just used these like the 3 big cities of northern Thailand and compare the model output to the observations in these areas. And then to let's say calculate the performance, I just use these following. So the bias, mean absolute error, RMS, and correlation coefficients between the model and the observations. So I looked at temperature, pressure, humidity, rain. But rain only during the wet season because I didn't have rain data during the dry season. And I calculated also the, I just modified a bit those equations to come up with a percentage values for each of these. So as you can see, I didn't include the wind and the wind speed and wind direction, mainly because so the setup that I use, so I didn't use any urban canopy model, which I plan to use maybe in the succeeding phase to get the, let's say, the wind better. Because usually the wind data will become, let's say, from weather stations or with an anemometer, let's say, placed somewhere here, and that's clearly in the urban canopy, and that will really have a different value with compared with the what the model is getting, because the models wouldn't have these buildings in there. So so I plan to use urban canopy model also in the next phase. So it was good in the workshop last Sunday. So there are a lot of people who are researchers who already use this urban canopy model. So this is just the framework. So basically, I'm just running. I just run the WRF model, and then change the microphysics, and then rerun it, and then calculate the bias compared to meteorological observations. Eventually, I will try, once I found out the best or the optimum parameters, I'll try that for the forecasting. So to run the WRF in the direct HPC, so I use the MPICH3. And one of the things that I discovered is because I'm not a computer scientist, and I thought that the more cores that you use, the faster your computation or will run. But I found out that there is actually just an optimum amount, let's say, of cores that you can use. So one of the things is probably like some of the processes. So for example, if in this case, let's say this process is quite fast. However, this process is quite slow, and let's say the output of this process will be used by another process, then it has to wait. And maybe that's also one of the things that might be responsible why not necessarily that if you use more cores, that does not necessarily mean it would be faster. So I had to look into what is the optimum number of cores, at least for the time period, the parameterization that I use would be fast enough. So I found that just using 8 cores is actually faster than using 16 or 32. So this is just an example, some of the output of the model. So this is during the full dry season. So this is for 2-kilometer grid, and using this parameterization for microphysics and convective or cumulus parameterization. So that's how it looks like. But this is the temperature, so you can see clearly the diurnal variation. For the hot dry season, this is just an example of, let's say, the water vapor mixing ratio. Okay, at 50 kilometers, this is at 50 kilometers, using this microphysics and cumulus parameterization scheme. And then this is the accumulated non-convective rain, okay, for the wet season. So this is just some example. So if I look at the individual stations, so for example, this is at Chiang Mai Airport from the Thailand department station. So this is just an example of how the time series would look like and how it would compare with the observation. So this is for the temperature, this one is for the pressure, this one is for humidity, this one is for rain. But as you can see, there's not much data. Oh, actually, yeah, there's not enough data there. And as you can see, what I was pointing out a while ago, so the wind speed and wind direction, so they're really quite off. So because the observations are probably inside the urban canopy, but the model doesn't pick this up. So just ignore the winds for now. So I also looked at the correlations between the observation on the X and then the model output. So this one is for temperature, pressure, humidity, so rain, as you can see, it's not enough data. So for this season, and so on. And then I looked at, so I did this for all the parameterization combinations, and found out for the cool dry season, so I just looked at the minimum, let's say the minimum bias. So in this case, the minimum bias somewhere here, and then the other metrics, so the mean absolute error, and so in this case, for these two metrics, so this microphysics and cumulus combinations have the smallest errors, and this one is for the root mean square. Okay. But for the correlation, so it's actually a different parameter. But I just looked at, let's say, how much, let's say, the MP3C1. So 3 out of 4 four metrics. So it was the smallest. So I did this for the other seasons as well, and it turns out that it seems there's some like seasonal the parameterizations that have some seasonal component. Like for example, for the cool dry season, it seems it's this parameterization compared to observations to have the smallest errors. For the hot dry season, it's this, and then for the wet season, it's this parameterization combination. So I also tested it for like resolution, like which resolution is better, because we always have the notion that the higher the resolution, the accurate it should be. Okay. However, I found out. So I was also surprised that it was not that necessary that the higher the resolution, the more accurate, or if you compare it to observations, it would be. And I'm still trying to find out like what are the reasons why, let's say, that's the case. So this is for the cool dry season, so it's okay. For the cool dry season, it seems the 2 kilometer resolution seems to be the best. However, so this is the 2, and I just compared with the 50 kilometer. So just skip this. But for the wet season, for example, I found out that actually it was the larger resolution that had the least error. So I'm still finding out the reasons why. So if anyone here has some idea why it could be, then that would be appreciated. So here, for example, for the wet season, the best seemed to be the 50 kilometer. And I looked at the time series, so this is using the 2 kilometer. So this is how it looked like. And then for the 50 kilometer, as you can see, also particularly for the rainfall. So again, this is the 2 kilometer. So you have these. So the red one is the model, the blue one is the observations. But for the 50 kilometer, it seems the model was closer to the observations at 50 kilometers. Also for the other parameters. However, for the pressure, of course, it would be very different. But it seems it could just be like a scaling. Because if you look at, let's say, at 50 kilometers, if you look at the correlation, so it's still quite tight here. It's just some bias that you have, for example, for the pressure. Okay, so for the different resolutions, so seeing the 2 kilometers is good for a cool dry season. 50 kilometers is based on comparing with observations. So the 50 kilometer resolution seemed to be had the least error during the hot, dry, and wet seasons. So in summary, so there seems to be some seasonal component. Which one is the best for optimum resolution? Microphysics and Cumulus. So these are the main results. And so this one is for so I just looked at during the cool dry season, the 2 kilometer seem to be better because it simulates temperature and pressure better than 50 kilometers. So these parameters or the model gets this better. And this one, including the rain during the wet season. So next steps, so using, let's say, those results, but I still want to look back and reevaluate those results. So I would like to apply them to the forecasting and maybe also look at, compare the model data with observed pro, let's say ranges on data, so we can also analyze the wind and also look at, let's say, the profiles of, let's say, water vapor, ice, and all that. And probably apply that to astronomical scene, because I think we're an astronomy institute, so at least have some astronomical applications as well. So for phase 2, so some recommendations for phase 2, maybe increase the number of validation sites. As you can see, I just used three validation sites to help 3 cities in terms of population, and utilize a longer temporal period. Also, because since we will be upgrading the cluster, so probably I could already use maybe, or I can try the longer time period, so hopefully it will have no problems with that. Also using a high resolution, and it will probably run better on the upgraded cluster. And also include maybe some urban canopy models to compare the surface winds, and also perform this what they call spectral and observational nudging, or basically it's simply similar to data assimilation. So using the observations to improve the models. And that's it. So thanks to all these people who contributed also to the research. Thank you.
Thank you very much. So do we have questions?
I just would like to say the high resolution, like the 2 kilometer, your wind speed consistently overestimate and the temperature, they underestimate or overestimate temperature and wind speed. I think the 2 kilometer, the first thing is that you need to consider if your land use classification is correct. And the second thing, because you see the simulation air temperature is actually underestimate compared with the observation, like the diurnal variation. And the second thing is that you need to consider in case you already run to 2 kilometers, maybe you need to consider the urban canopy effect. Would be and it will be improve the peak air temperature.
I think that's one way to improve the model.
And another comment, you use the 50 kilometer to simulation. You might know the NSEP, the NSS data already can provide 50 kilometer resolution. I think that you need, you can save some computer resources because you can use the more high resolution global model data to do information.
You mean for the boundary conditions?
Yeah. You just use the NSEP to NSEP. You use the 50 kilometer resolution. Yeah, because they already provide. And maybe we define it with resolution in the near future, 25 kilometer.
I think they already have some. Well, at least for the forecast, I think they have for the GFS forecast have some 25 kilometer resolution. Thank you for those suggestions.
Other questions? I do have one suggestion. You had the vapor visualization tool. Well, actually, there is a 3D visualization available in the latest version. So that should be, I assume, working on head-mounted display quite easily.
You mean?
If you look up the latest version of that software, and then you could load in your stuff, and then you should be able to see that version of it.
Well, that would be nice to see.
Yeah, I just checked it again. That is a version of software from October last year. So it's pretty new. Okay, thank you very much again. And now we have to see how we, my little helper needs to help me get to the laptop again. I'm not sure. need to do?